A very good day to everyone. I'm Ellen, and today me and my group members, Nora, Denisa, and Abu from Group Kk2 will be presenting our integrated project with the title of Production of Caprolactam. First and foremost, let me pass it to Nora for our introduction.
Caprolactam is an organic compound with chemical formula CH2,5CNH. According to Granville research, 30% of caprolactam is used for production of nuanced fiber with various end products. Caprolactam is widely used in textile, industrial, engineering, plastic, and carpet fiber industry. Around 48.3% of caprolactam is dominated by textile that is extensively used in numerous applications including apparel and house furnishing. Caprolactam are synthesized from cyclohexanol, which is first will be converted to its oxide and then treated with acid to induce pigment rearrangement forming caprolactam. These are some physical and biochemical properties of caprolactam. Rearrangement of cyclohexanoxime in R101. Cyclohexanoxime is rearranged by Beckmann rearrangement in the presence of oleum for the conversion of the oxime to caprolactam sulfate. The process takes place in continuous stem reactor (CSTR) at 125 degrees Celsius under atmospheric pressure. Cyclohexanoxime stream 2 and oleum from stream 4 is added into the reactor for the rearrangement to occur. A crude epsilon caprolactam reaction mixture containing caprolactam sulfate and sulfuric acid is obtained. Next, neutralization of rearrangement mixture in R102. The product formed from the acid-induced rearrangement is the bisulfate salt of caprolactam. The lactam mixture that contains caprolactam sulfate in stream 6 undergoes neutralization with aqueous ammonia, stream 8, in a stirring reactor of a pressure of 1 atmosphere. Caprolactam ammonium sulfate and water are formed from this process. Next, separation of caprolactam and ammonium sulfate salt in S101. The product enters the separator stream 9 to be separated. The ammonium sulfate and organic substance produced the neutralization process in stream 10 should be extracted from the lactam product. Benzene from stream 12 is added as a reagent to separate caprolactam from organic substance and ammonium sulfate. Caprolactam enters the extractor, stream 10, while ammonium sulfate and liquid waste are removed from the process through stream 4 through downstream. Purification of caprolactam in E101. The aqueous caprolactam solution is purified by extraction stream 14 with benzene in the extracted column E101. Benzene is added again stream 15 as a reagent from the purification process. Under high temperature, benzene will exit the extractor at the overhead stream 18 where it will be condensed to be stored back at the benzene storage vessel. This process happens at 4 bar and full vacuum at 115 degrees Celsius. Next, ion exchanging process I101. The caprolactam solution will undergo further purification to obtain a higher purity of product. The 30% purity caprolactam solution, stream 18, undergoes further purification through an ion exchanger method in an ion exchange bed and the purity increased to 85%. And lastly next is evaporation V101. Caprolactam solution, stream 20, is transferred to an evaporator to remove water and form solid caprolactam. The 85% concentration caprolactam solution, stream 21, will go through 3 evaporator stages in order to remove water at 135 degrees Celsius and 2.8 bar pressure, resulting to 99.9% caprolactam concentration. During this process, excess water will be released through the upstream as water vapor, stream 22, and the final product, which is caprolactam, is obtained in stream 23.
Next is the economic issues, where based on the demand and supply of caprolactam from year 2019 to year 2024, we obtained that the supply is 816,698 kilotons per year and the demand is 862,356 kilotons per year. So for the plant capacity, the design of caprolactam production is aimed to produce 2,380.74 tons of caprolactam annually, and the plant will operate 350 days per year, with 15 days left is used for cleaning and maintenance process for the machine in the factory, and the final production rate is estimated to be 271.774 kg per hour as shown in the calculation.
Waste generation. From the process of production of caprolactam, the main waste generated, stream 14, are liquid and organic waste, like ester, cyclohexanoxime, caprolactam sulfate, and sulfuric acid. As for benzene, from stream 19, discharge from the process is flowed to storage for future usage in the process. Ammonia sulfate in stream 14 can be sold to other industries that may require them as raw material in some production. Water vapor from stream 22 and liquid waste from stream 14 is treated by wastewater treatment. Wastewater treatment. There are three stages in wastewater treatment, including primary, secondary, and tertiary treatment. Firstly, screening and straining process is crucial to remove small particles, including grease, to make sure it does not infect equipment. Wastewater will flow through bar screen, and once it's done, chemical coagulants, which is aluminium sulfate, is added that reacts with natural alkalinity in solution to suspend particles that are floating, forming larger gelatinous particles called floc. Next, water then flows into sedimentation basin, where water makes its way to the center of clarifier while large floc particles settle out to the bottom of clarifier and is sent to disposal ponds. Water passes over the where is transferred to the filter. Granular activated carbon is used as the media of choice for filtration because it provides excellent mechanical filtration of particles, matter, and remove organic compounds. The next stage is to significantly degrade the biological content in water, which is benzene. The water is pumped into aeration basin along with return activated sludge, RAS. This introduction of significant amounts of bacteria along with massive amount of oxygen injected from the bubbles creates an environment perfect for the process of aerobic digestion. This is a biological process of breakdown of organic matter using excess oxygen. The last step is disinfection. During this stage, chlorine is added to kill off remaining bacteria and organisms that are still remain in water. Chlorine then has to be removed before it can be discharged, so it is neutralized by using some chemicals. At this point, water should be safe to be discharged to stream or lakes.
Good day. I will continue on the material balance while Abu will explain on the energy balance. Let's take continuous stir-tank reactor R101 as our example. First, we assume that the basic feed rate of cyclohexanol oxygenate is 100 kmol per hour, while for volume is 99 kmol per hour are fed into the tank reactor. The fractional conversion of cyclohexanol oxygenate is 0.99. Next, the extent of reaction of 99 kmol per hour is obtained by multiplying conversion rate and the basis flow rate of cyclohexanol oxygenate. Using equation where molar flow rate in subtract the extent of reaction equals to molar flow rate out, the mole flow rate of each component can be obtained. The mass flow is obtained by multiplying mole flow rate by its molecular weight. By using the concept, total mass flow in equals to total mass flow out, our calculations are shown balanced with total flow rate of 28,952 kg per hour for both inlet and outlet. At the end of all calculations, the flow rate of each component in the process is scaled down by scale factor of 39.945 in order to achieve our plant capacity of 271.77 kg per hour.
Next, I will proceed with the energy balance. For the production of caprolactam, we calculate the energy balance for 3 unit operation, continuous state tank reactor, evaporator, and also another state tank reactor. Before we do the calculation, we need to know the heat capacity and also the heat of formation of each component. So here is the table that shows all the information. For example, I will explain the energy balance of continuous state tank reactor. So here is the equation. We also need to know the inlet temperature for stream 2 and 4, which is 328.15 Kelvin and 318.15 Kelvin, while the outlet temperature for stream 5 is 333.15 Kelvin. By integrating the heat capacity Cp, we can calculate the enthalpy delta H. After we get the value of inlet and outlet enthalpy, we can obtain the delta H reaction, which is negative 616.589 kJ per mole. The rate of reaction R is 99 kmol per hour. We can obtain the value of Q by using the formula and we get negative 76966.29 kJ per hour. The negative sign indicates that the reaction in continuous state tank reactor is exothermic reaction. It means that the process releases heat. The method of calculation is the same for evaporator and also another stirred tank reactor. The difference is the value of Q obtained for both evaporator and the stirred tank reactor is positive. It means that they are endothermic reaction and the process absorbs heat.
For the heat and mass transfer, we focus on the continuous stirred tank reactor R101. From the calculation, we obtain that the Reynolds number is 439.4, which is less than 2400, thus the flow is a laminar flow. The overall equation of heat transfer through cylindrical reactor is obtained by using the formula below, and the final heat transfer rate is 197.91 watts, which conclude that the reaction is an endothermic reaction. Next is the mass transfer. Below are the factors influencing the mass transfer rate, which are molecular diffusivity, concentration gradient, convective mass transfer coefficient, and distance of diffusion. So the molecular diffusivity, concentration gradient, and convective mass transfer coefficient, all three are directly proportional to the mass transfer rate, where when the molecular diffusivity, concentration gradient, or convective mass transfer coefficient increases, the mass transfer rate increases too. Whereas the distance of diffusion is inversely proportional to the mass transfer rate, where the smaller the distance of diffusion, the higher the mass transfer rate. The diffusivity DAB is determined by using the Stokes-Einstein formula, where the major component at point 1 and point 2 are caprolactam sulfate and caprolactam. The temperature of the reactor is 343.15 Kelvin and the pressure is at 1 atm. And the diffusivity that is obtained is 1.1025 times 10 to the power of negative 10 meters square per second. Next, the rate of mass transfer can be expressed as flux in terms of Fick's law. Once the value is inserted into the Fick's law, the final flux obtained is 5.244 times 10 to the power of negative 11 kilogram mole per second meter square.
Continuing to chemical reaction engineering part, our reactor selection for our reaction is continuous stirred tank reactor, CSTR. This is due to our process mainly involves liquid phase reactants under steady and continuous process. CSTR is commonly used in homogeneous liquid phase for reactions. Oleum is used as solvent and catalyst in this process. The byproduct produced in the production of caprolactam is ammonium sulfate. Next, the general mole balance equation for CSTR is obtained after making some assumptions like the reaction is in steady state conditions and the reactants are perfectly mixed with constant volume. There is also no product accumulation left in the system. After reducing and rearranging the equation shown in the report, the general mole balance obtained is as shown in the slide. Lastly, the kinetic rate expression is needed to obtain the final rate law. First, a stoichiometric equation of the rearrangement reaction is needed. Species A is taken as basis, and the rate law R equals to K CACD is obtained after calculating the reaction stoichiometry. The inner rate, changes in rate, influent rate, and concentration are all shown in the table. Final rate law, R equals to KCA0 squared times 1 minus X times delta B minus F is obtained by substituting concentration into the rate law. That's all from me. Thank you.
Next, I will proceed with MATLAB. We use MATLAB to calculate the mass balance and at the end, we manage to compare with manual calculation. So, this is the flow chart. We begin with start and set the rate of reaction R. We want to calculate and compare the value for continuous stirred tank reactor, so we use rate of reaction equal to 99 kmol per hour. Next, we fix the stoichiometry and also input the molar flow rate for cyclohexanone and also oleum. Then, set the molecular weight of each component including caprolactam sulfate and sulfuric acid. If the inlet flow rate less or equal to 0, it will display error because the inlet flow rate must be positive value only. Next, we compute the outlet flow rate of each component and convert it to mass flow rate. Lastly, tabulate and display the inlet and outlet mass flow rate and also total inlet and outlet mass flow rate. From the command window, we need to enter the value of inlet molar flow rate of cyclohexanone and also oleum. After that, we obtain the mass flow rate of each component in continuous stirred tank reactor, and the result shows that the total mass flow rate of inlet and outlet stream are balanced. After that, we do comparison for outlet mass flow rate obtained between manual calculation and also MATLAB. They are almost the same, The only difference is for sulfuric acid with only 0.0000103% error.
In conclusion, caprolactam is a clear to milky white colored synthetic crystalline compound with chemical formula C6H11NO. From the demand and supply, it is calculated that 2,380.74 tons per year is the plant capacity for this project in order to fulfill the global demand of caprolactam. The production of caprolactam will produce waste products such as wastewater, ammonium sulfate and benzene that are needed to be treated before it is released to the environment. The overall heat transfer rate Q is equals to 197.91 watts. By using the Stokes-Einstein formula, diffusivity is determined, which is 1.1025 times 10 to the power of negative 10 meters square per second. Therefore, the flux is 5.244 times 10 to the power of negative 11 kilogram mole per second meter square. Softwares such as SuperPro and MATLAB have been utilized to obtain and compare the values of mass balance and energy balance. The type of reactor used is a continuous stirred tank reactor CSTR. Thank you.